everyone, कैसे हो आप सब? Welcome you all to the online session of Gurukul Academy. I hope you all are doing good. So let us begin with the today's class. So today our topic is going to be superconductivity, a very important and very interesting topic it is. So let us start with the today's lecture and let us study about my favorite topic, that is superconductivity. Okay, so what is superconductors? What is superconductivity? What does this term means? Let us study in the today's class. So, superconductors. Superconductors. What are superconductors? क्या होते हैं ये superconductors? आइए जानते हैं हम आज की क्लास में कि ये superconductors होते क्या हैं. तो superconductors बच्चे आपके पास ऐसे materials होते हैं which have infinite resistance, which have infinite conductivity, and zero resistance, superconductors बच्चे हमारे पास वो वाले materials होते हैं in which the conductivity, that is the sigma approaches to infinity and the resistivity that is approaches to zero. Resistivity approaches to zero and the conductivity approaches to infinity. Those type of materials are known as superconductors. Whenever you cool down the conductors below a critical temperature, the material becomes superconducting in nature and they are very useful for us. So now let us study in detail that what are these superconductors, how they are formed, what is type 1 superconductor, what is type 2 superconductor, what is the physics behind this superconductor. In a very interesting way we are going to study this lecture. So now let us begin. What are superconductors actually? First of all, please take your copy and pen and makes the beautiful note of the topic of superconductors कि ये होते क्या हैं, ये काम कैसे करते हैं. So first of all, write the definition of superconductors. Write down, superconductors are the materials which have infinite conductivity and zero resistivity. Okay, and it was found that at very low temperature, most of the metals, actually what was the concept that at very low temperature, it was found that some metals lose their resistance totally. Okay, whenever you reduce the temperature to a particular low value, what you will find out, that some metals lose their resistance totally and they become superconductors. It means they start to conduct in a very effective manner. There is a infinite conductivity and that phenomena is known as the superconductive phenomena and the materials are known as superconductors and they allow the current to pass through them and the phenomena is superconductivity. Okay, the temperature at which the resistance suddenly falls to zero is known as critical temperature. So what is the term? The term is critical temperature. The temperature, what is critical temperature? The temperature at which resistance falls to zero. The temperature at which the resistance falls to zero is known as critical temperature. Okay, that is TC. Because let us draw the graph between these two. ग्राफ बना के दिखाती हूँ मैं आपको. अब देखो, अगर मैं ग्राफ ड्रॉ करूँ नॉर्मल कंडक्टर्स के लिए एंड सुपर कंडक्टर्स के लिए, लेट सपोज एक ही ग्राफ पे मैं ड्रॉ कर लेती हूँ. यहाँ है मेरी रेजिस्टेंस, here is my resistance and here is my temperature and here is our temperature. Okay, यहाँ टेम्परेचर है, यहाँ रेजिस्टेंस है. अब अगर मैं नॉर्मल कंडक्टर के लिए बनाना चाहूँ, लेट सपोज यहाँ पर 4.0 से शुरू हो रहा है कुछ 4.1 एंड 4.15 समथिंग. सो लेट अस सपोज दैट अगर मैं नॉर्मल कंडक्टर के लिए ग्राफ बनाना चाहूँ, सो इट इज लाइक दैट. दिस इज फॉर नॉर्मल कंडक्टर, दिस ग्राफ इज फॉर नॉर्मल कंडक्टर. बट सुपर कंडक्टर के लिए ग्राफ ऐसा नहीं आता है. यू कैन सी normal conductor have finite value of resistance. Normal conductor have finite value of resistance. Finite value of resistance. But if I draw the graph for superconductor, so वो ग्राफ कैसा आता है, चलिए आइए वो देखते हैं कि सुपरकंडक्टर्स के लिए बच्चे ग्राफ कैसा आ रहा है. सुपरकंडक्टर्स lose their resistance at a particular temperature Tc. So let us suppose this is the particular temperature 4.15, this is the particular temperature 4.15 at which the superconductor lose their resistance totally. For example, this is the graph for superconductors, this is the graph for superconductors. But when superconductors are cooled down to a critical temperature Tc, they lose their resistance. They lose their resistance and their resistivity approaches to 0 and their conductivity approaches to infinity. So this is the differentiate between the graph. And the question comes to our mind is whether the resistance of superconductor actually becomes 0 or not. So we can set up a current in a superconducting ring and we can observe that the current decays or it does not decay. So we can do this experiment in order to determine whether the resistance is seriously 0. So you find out that current does not decay with time. In superconductors, current does not decay with time. In superconductors, current does not decay with time. In superconductors, the current does not decay with time. So that means, what does it mean? It means the current is known as persistence current and the current produces a magnetic field, and the presence of this magnetic field for years proves that the resistance of superconducting material actually becomes 0. Okay, and it produces the magnetic field Okay, this is known as the persistent current. This is known as the persistent current and it produces the magnetic field, and it proves that the resistance of superconductors actually become 0. Resistance of superconductor actually become 0. Okay, जो रेजिस्टेंस होती है सुपरकंडक्टर की, इट एक्चुअली बिकम 0. ओके, क्लियर है यहां तक सभी को? यस एवरीवन, प्लीज टेल मी, यहां तक सभी को समझ आया? So superconductor which show the phenomena of superconductivity even at the high temperature, they are known as the हाई टेम्परेचर सुपरकंडक्टर्स. कुछ सुपरकंडक्टर्स हमारे पास ऐसे भी हैं जो हाई टेम्परेचर पे सुपरकंडक्टिविटी का फिनोमिना दिखाते हैं, उनको हम हाई टेम्परेचर सुपरकंडक्टर्स बोलते हैं. सो नाउ लेट अस राइट सम प्रॉपर्टीज ऑफ सुपरकंडक्टर. व्हाट आर प्रॉपर्टीज ऑफ सुपरकंडक्टर्स? तो इसमें वैसे तो काफी सारी प्रॉपर्टीज आ जाती हैं. तो सबसे पहले तो ना आपको पता होना चाहिए that superconductors are diamagnetic in nature. First thing जो आपको अच्छे से पता होना चाहिए, वो आपको पता होना चाहिए कि superconductors जो होते हैं वो diamagnetic होते हैं नेचर में. Superconductors are डायामैग्नेटिक इन नेचर, क्योंकि ये शो करते हैं मीजनर इफेक्ट. अब मैं आपको डिटेल में पढ़ाऊंगी कि मीजनर इफेक्ट होता क्या है, बट आपको पता होना चाहिए दैट सुपरकंडक्टर्स आर डायामैग्नेटिक इन नेचर एंड दैट इज प्रूवन बाय द मीजनर इफेक्ट. वो हम अभी डिटेल में पढ़ेंगे कि मीजनर इफेक्ट आखिरकार होता क्या है. तो यहाँ तक अभी इंट्रोडक्शन मैंने जो दी है सुपरकंडक्टर्स की, आई थिंक वो आपको क्लियर होगी कि सुपरकंडक्टर्स बच्चे होते क्या हैं. Superconductors are those materials which show infinite conductivity but zero resistance at very low temperature. Actually, what was observed that when we go to a very low temperature, some materials lose their resistance totally and they start behaving like superconductors. Means there is a persistent current in them. The current does not decay with time, which shows that actually the resistance becomes 0 in superconductor. For example, let us show the graph between the resistance and the temperature For normal conductor, you can see for normal conductors, there is always a finite value of resistance even when the temperature approaches to a very, very low value. But you can clearly see that for superconductors, as we approach a particular low temperature Tc, that is the critical temperature at which the superconductors have zero resistance, below which the superconductors have zero resistance. It means they start behaving like a infinite conducting materials. So you can see the difference between two graphs. When we cool down to Tc, superconductors lose their resistance totally, but there is some finite value of resistance for the normal conductors. So you should remember that in superconductors, current does not decay with time and it produces a magnetic field, which results that the resistance of a superconductor is seriously zero. And the superconductors are diamagnetic materials. Superconductors do not allow the magnetic field of lines to pass through them. They do not allow the magnetic field of lines to pass through them. They expel out the magnetic field of lines. When you place the superconductor in the magnetic field, they do not allow the magnetic field of line to pass through them. They expel out the magnetic field of line, and as a result, we say that the superconductors are diamagnetic in nature, and the process is known as Meissner effect. Okay. Now let us study the isotopic effect of superconductor. So first of all, let us study the isotopic effect of superconductors. So what is isotopic effect? What is the isotopic effect of superconductors? हाँ जी, क्या होता है आइसोटॉपिक इफेक्ट ऑफ सुपरकंडक्टर्स, बता सकते हो? व्हाट इज द आइसोटॉपिक इफेक्ट ऑफ सुपरकंडक्टर्स? एनीवन? वैसे तो आपने पढ़ा हुआ है पहले ये. हाँ जी, yes, very good. Okay. Superconductors vary, the critical temperature of superconductor vary with their isotopic mass. What is the isotopic effect? The critical temperature of superconductors, the critical temperature of superconductors varies with the isotopic mass. That means as the mass increases, what is the statement of this isotopic effect is that critical temperature into isotopic mass under root is equal to constant, and that means the critical temperature decreases as the isotopic mass increases. What is isotopic effect says? That the critical temperature is inversely proportional to the isotopic mass. Critical temperature decreases as the isotopic mass increases. So as we replace the isotope with the heavier one, so its critical temperature will decrease. So it will reach the superconductive phenomena at a lower critical temperature. So graph will be like this. So between log Tc and logarithmic of atomic isotopic mass, the graph will be like this. Okay, the variation will be like this. Clear all of you? So effect some clues about the establishment of the theory of superconductivity. It is well known that the mean square amplitude of lattice vibration is also proportional to m raised to -12. That is, heavier isotopes have lower lattice vibration. You should also know that heavier isotopes has lower lattice vibration. Lattice vibration is also directly proportional to m raised to power -12. That is, heavier isotope also have lower lattice vibration. So it has direct consequence of the superconductivity, that we can learn more about the superconductivity. That heavier isotopes have the lower lattice vibration. So it is well known that Debye temperature theta d of the phonon is also proportional to m-12. जो हम करते हैं ना Debye temperature के बारे में जो हम पढ़ते हैं, theta d, that is also proportional to m-12. Okay, like here Tc is also proportional to m minus half. Critical temperature and Debye temperature both have the same variation with the isotopic mass. Okay, so the relation suggests that the lattice vibration must be related to superconducting state of the material. This shows that the lattice vibration must be connected with the superconducting state of the material. Okay, clear all of you? So electron phonon interaction is responsible for the superconducting phenomena. तो यहाँ से हमें पता लगता है इलेक्ट्रॉन phonon interaction is responsible for superconducting phenomena. अब ये जो superconducting phenomena के पीछे हाथ किसका है वो हमें यहाँ से पता लगा that it is because of the electron phonon interaction. It is because of the electron phonon interaction that is responsible for the superconducting phenomena. क्लियर है यहाँ तक सभी को? तो आइसोटॉपिक इफेक्ट बच्चे आपको क्या कहता है, चलिए आइए देख लेते हैं एक बार. आइसोटॉपिक इफेक्ट इन द सुपरकंडक्टर्स टेल्स यू दैट, हाँ कोई डाउट है? Okay. So isotopic effect in the superconducting phenomena says that the superconductors have their critical temperature Tc that varies inversely with the isotopic mass. That is, the m half is inversely proportional to the critical temperature. As the critical temperature decreases because the isotopic mass increases. If the isotopic mass increases, the critical temperature decreases. And heavier isotopes has also lower lattice vibration. We all know that the heavier isotopes have the lower lattice vibration. It means the lattice vibration is interrelated with the superconducting phenomena. All right, lattice vibration is interrelated with the superconducting phenomena. So that means the electron phonon interaction is responsible for the superconducting phenomena. यहाँ तक सबको बात क्लियर हो गई है? हाँ जी बताइए. चलिए अब हम बात करते हैं क्रिटिकल मैग्नेटिक फील्ड के बारे में. नाउ लेट अस टॉक अबाउट द क्रिटिकल मैग्नेटिक फील्ड. व्हाट इज क्रिटिकल मैग्नेटिक फील्ड? It is observed that if superconductor is placed in significantly strong magnetic field, the superconductor becomes a normal conductor. If we place the superconductors in very strong magnetic field, so superconductors become normal conductor. So superconductors become normal conductors. Okay. तो जैसे ही हम उनको रखते हैं इन अ वेरी स्ट्रॉन्ग मैग्नेटिक फील्ड, इन अ सफिशिएंटली स्ट्रॉन्ग मैग्नेटिक फील्ड, so their resistance again come into picture and they become the normal conductor. Resistance again come into picture and they become the normal conductor. जैसे हम सुपर कंडक्टर को एक sufficiently strong magnetic field में रखते हैं तो आपके जो सुपर कंडक्टर्स हैं उनमें रेजिस्टेंस दोबारा से आ जाती है और वो दोबारा किस में कन्वर्ट हो जाते हैं? नॉर्मल कंडक्टर्स में कन्वर्ट हो जाते हैं. और उस मैग्नेटिक फील्ड को हम क्या बोलते हैं? क्रिटिकल मैग्नेटिक फील्ड. ओके, एंड द क्रिटिकल मैग्नेटिक फील्ड इज अ फंक्शन ऑफ टेम्परेचर एंड यू शुड रिमेंबर दैट critical field is a function of temperature. Critical field is a function of temperature. Okay, so HCT is given by HC naught 1 minus T square over TC square. This is the formula that critical field varies like this. HCT, that is HC naught is the critical magnetic field at 0 Kelvin. Okay, एंड HCT इज क्रिटिकल मैग्नेटिक फील्ड एट टेम्परेचर T. तो अगर हम ग्राफ ड्रॉ करना चाहें तो कुछ इस तरह का ग्राफ आता है. तो कुछ इस तरह का ग्राफ देखने को मिलता है. Okay, this is the temperature and here is the Hc. So Hc is equal to Hc naught 1 minus T upon Tc whole square. Clear all of you? So this is the superconducting state and outside it, it is the normal conducting state. ठीक है? ठीक है जी, यहां तक सबको क्लियर हो गया है. Now let us talk about the Meissner effect. Now let us talk about the Meissner effect. What is Meissner effect? Superconductors show perfect diamagnetism. I told you already, superconductors shows perfect diamagnetism. Superconductors shows perfect diamagnetism. Alright, superconductors are perfectly diamagnetic. They expel out the magnetic field lines out from them and they do not allow the magnetic field lines to pass through them, and they show the phenomena of superconductivity. That is the Meissner effect. That is, superconductors are diamagnetic in nature. So you can write down in 1993, Meissner found that superconductor expels the magnetic flux. Superconductors expels the magnetic flux. Superconductor expels the magnetic flux as the Tc is reached. जैसे ही हम Tc critical temperature पे पहुंचते हैं तो superconductors expels the magnetic flux and this means that superconductor behave as perfect diamagnet. The phenomena of expelling out of magnetic flux is known as Meissner effect. ये जो phenomena है to expel out all the magnetic flux out of them, उसी को हम क्या बोलते हैं? Meissner effect बोलते हैं. तो Meissner effect और कुछ नहीं, it is a phenomena to expel out all the magnetic flux out of them as the soon critical temperature is reached. Clear? So in superconductors we see the perfect diamagnetism. Clear all of you? In superconductor we see there is a perfect diamagnetism, that is B is equal to mu naught H plus M. Alright, B is equal to mu naught H plus M and it is equal to 0. There is no magnetic field present inside the superconductors. That means H is equal to minus M. That means H is equal to minus M. And when H is equal to minus M, susceptibility is negative because it is the ratio of M by H. So susceptibility is negative for superconductors. It can be asked in the exam. So perfect diamagnetic substance are superconductors with the susceptibility negative. Clear all of you? Now let us move to the next topic, that is London equations. What are London equations in the superconducting state? What do you mean by London equations? Yes. अच्छा चलिए पिछला नोट कर लीजिए, कोई बात नहीं. So according to Meissner effect बच्चे, the magnetic flux is pushed out of the body of the superconductor at transition temperature, you know, है ना. अच्छा एक बात हमेशा ध्यान रखो, in superconductor E is equal to 0, E is equal to 0 and B is equal to 0 in superconductor. This can be asked in your exam. In superconductor E is equal to 0 and B is equal to 0. Okay, E and B both are 0 in the superconductors. Now let us discuss about the London equation. तो बच्चे मैंने आपको बोला कि magnetic flux जो है that get pushed out है ना from the interior of the superconductor, but it is not like just zero, एकदम से zero. It is not the case. What is actually happening? Magnetic flux decay from a constant value at the surface to zero value in the interior, but the decay is gradual, not abrupt. The decay of magnetic flux is gradual, not abrupt. Abrupt decay नहीं है, it is a gradual decay that is from some value from the exterior to 0 in the interior. It is a gradual decay and the distance of penetration below the surface is of 500 angstrom. Okay, so in order to explain the phenomena of flux penetration through thin films of superconductor, we devise some equations और उनको हम क्या बोलते हैं, लंदन इक्वेशंस बोलते हैं. Okay, superconducting state में current density is directly proportional to vector potential A. In superconductors, the current density, that is the current density is directly proportional to vector potential A. ये क्या होती है, current density. What is this? This is the current density and what is this? This is the vector potential. आपको पता है B is equal to del cross A, तो है ना, ये वही वाली vector potential है. That is, और इसको हम लिखते हैं by introducing a constant mu naught this. Okay, and this is the constant of proportionality. और ये जो lambda L है, this is known as London penetration depth. This is known as penetration depth. This is known as penetration depth. Okay, so what is London equation? आप इसका कर्ल ले सकते हैं. You can take the curl of JS. Okay, अगर हम इसका कर्ल ले, if we take the curl of JS, so that will be equal to minus mu naught curl of A. So that means curl of JS is equal to minus mu naught. This is what? This is B vector. This is the B vector. B is equal to del cross A. All right. ठीक है, यहां तक सभी को क्लियर हुआ? एंड यू शुड नो, और आपको अच्छे से पता है कि डैट B क्या होता है, B क्या होता है, B इज व्हाट, म्यू नॉट J, है ना. स्टैटिक कंडीशन से वी नो B इज इक्वल टू म्यू नॉट JS एंड कर्ल ऑफ कर्ल B. व्हाट इज कर्ल ऑफ कर्ल B? कर्ल ऑफ कर्ल B इज इक्वल टू म्यू नॉट कर्ल ऑफ J. अगर मैं दोनों तरफ कर्ल ले लेती हूं, है ना, तो एंड व्हाट इज कर्ल ऑफ कर्ल B? दैट इज इक्वल टू ग्रेडियंट ऑफ डाइवर्जेंस ऑफ B. यहां पे लिखती हूं ग्रेडियंट ऑफ डाइवर्जेंस ऑफ B इज इक्वल टू सॉरी, कैसे खोलते हैं हम इसको, कर्ल ऑफ कर्ल B को हम कैसे खोलते हैं, ग्रेडियंट ऑफ, देखो कर्ल ऑफ कर्ल B, ये आपको पता है, कर्ल ऑफ कर्ल B, इसको कैसे खोलते हैं, first is del dot B, gradient of divergence of B and minus del square B. Minus del square B is equal to mu naught curl J. Mu naught curl J. यहां तक समझ आया? अब आपको पता है divergence of B is always 0. So that means curl of B is equal to mu naught curl of J. Right? ठीक है यहां तक? हाँ, माइनस भी है यहां पर, बिल्कुल सही. अब वैल्यू को सब्स्टिट्यूट कर दो, कर्ल ऑफ J हमें पता है, दिस इज द वैल्यू ऑफ कर्ल ऑफ J. सो व्हाट यू गेट द फाइनल इक्वेशन? फाइनल इक्वेशन क्या मिली, बोलो, फाइनल इक्वेशन सब्स्टिट्यूट करो, सब्स्टिट्यूट इट हियर, यहां पर सब्स्टिट्यूट करो और मुझे बताओ कर्ल ऑफ B की फाइनल इक्वेशन आपको क्या मिल रही है, दैट इज B वेक्टर अपॉन लैम्डा L का स्क्वायर. दिस इज द फाइनल इक्वेशन यू आर गेटिंग. इजीली मिल जाएगी, कोई दिक्कत वाली बात नहीं है. And this equation does not have a solution uniform in space. Hence a uniform magnetic field cannot exist in a superconductor. यहाँ से हमें एक और बात पता लगी, uniform magnetic field cannot exist in superconductor. You can write down this point. And what is the solution of this equation? What is the solution of this equation? That is BZ is equal to BZ naught e raised to power minus x by lambda L. This is the solution of this equation. What is the London equation? Del square B is equal to B upon lambda L square. And what is the solution? BZ is equal to BZ naught e raised to power minus x upon lambda L, where BZ naught is the value of magnetic field at the boundary of slab. Okay, at the boundary of slab. Hence the field decay exponentially. आपको पता लगा कि यहां पर फील्ड कैसे डिके कर रहा है, मैग्नेटिक फील्ड इनसाइड दैट सुपरकंडक्टर डिकेज एक्सपोनेंशियली. like this. This is the value of magnetic field at the slab, and this is how the magnetic field is decaying. The magnetic field is decaying exponentially, and let us draw the graph. कुछ इस तरह का ग्राफ आता है. Here is BZ naught at the boundary. Here it is BZ naught, and there is a कैसे decay है बोलो, and there is a exponential decay. Exponential decay. Okay, here let us suppose inside it is a bulk specimen. There is a exponential decay. ये बीच में क्या है? It is a bulk specimen, and you can say this is exponential decay. The magnetic field is not decaying abruptly inside the superconductor, but it is decaying exponentially. It is decaying exponentially. ठीक है, यहां तक सभी को क्लियर हो गया है? हाँ जी बच्चे बोलिए, सबको क्लियर हो गया है? द मैग्नेटिक फील्ड इज डिकेइंग एक्सपोनेंशियली. All right, please note down carefully. The exponential decay. There is an exponential decay. हाँ, ये वाला पेज अच्छे से नोट कर लीजिए सब लोग. Yeah.